Welcome to this video on theoretically deriving an equation for an oscillating spring. Now, what we have here is a spring that's attached to a box, and the box is the object that we're focusing on here. The mass of the spring is negligible compared to that of the box. And what we're going to take a look at here is if we can come up with an expression for all the kinds of motion, or many different descriptions of the kind of motion for this oscillating box. So the first thing I want to do here is take a look at conceptually or physically what is happening. So if I pull the box this way, it reaches some maximum point over here, and then the spring pulls it back. Because the spring has been stretched, it pulls it back, it passes through equilibrium, and it will reach a distance on this side that's the same as this, and because it's compressed the spring is going to push it back, and that will continue to happen back and forth. Now, of course, we have not added damping to our model yet. We can add that a little bit later. But what we can say here is that the force, the net force acting on the spring at any given time, is the restoring force. And I'm going to tell you that this is a linear spring. So the restoring force is equal to negative kx. Now, it's a linear spring, which means that when the spring is stretched to a position x, the force pulls back with an amount of force that is directly proportional to that stretch. This makes this particular box here, or this particular system, a simple harmonic oscillator, or we could say that it's undergoing simple harmonic motion. And remember, that makes it a specific kind of oscillatory or periodic motion. Now, what we want to look at here is trying to relate this position function to the object's motion. So the position function here is not ever constant because we know that the position is changing. However, it does have a distinct pattern to it, and so we're going to try to see if we can solve for what that would be. So I'm going to come over here first to my x versus t graph, and I'm going to take a look here at what it might do as time passes. So I'm going to put the box over here at this maximum amplitude, and then I'm going to say that it passes through equilibrium, and then it's going to reach this maximum amplitude on the other side, pass back again through equilibrium, reach maximum amplitude through equilibrium, and maximum amplitude. And so what we're going to get here is this function that looks somewhat like this. Okay, now what we're going to do here is we're going to try to come up with a way to describe this function in other perspectives. So let's look at what's happening here with the velocity as a function of time. Now, what I want to do here is say that I know that the derivative of the position function with respect to time will give me a velocity function with respect to time. At any of the maxima or minima of this graph, I know that the derivative is equal to 0. So I'm going to go ahead and plot those specific points, and I'll go ahead and put them over here on this velocity versus time graph. Now I know that the maximum value over here is where the slope or the derivative is at a negative maximum value, so that will pull this down here. Here's a maximum positive value, another maximum negative value, and so on. So what I start to see here is that I have another transcendental or trig function that shows up looking something like this. Finally, let's take a look at when we do the derivative of the velocity function with respect to time, we get an acceleration function. Again, the derivative at all of these maxima or minima are going to give us zeros, and then we'll have a negative minimum here, a negative maximum at this position, and on and on. So when we graph this, we get something that looks like this. Now, the reason that I'm taking the time to sketch these out is because it's going to become very important to us when we're trying to theoretically derive a function here for the position. Now if you think about it, the position affects the force, and the force affects the velocity and or acceleration. So what we're going to have here is some sort of differential equation. And the differential equation can be found by setting up a net force statement. So I'm going to go ahead and do that over here. So I'm going to say that the restoring force, which I've said is negative kx, is equal to the net force, and I'm going to set that as m times a. Now I know that x of t this is a function. X is a function of time, and acceleration is going to be a function of x. So if I relate those two together, I get negative kx equals m times the second derivative of position, d squared x over dt squared. Okay, and there I have a differential equation that relates the two, or relates the position function to its second derivative. Now I'm going to divide by the mass so I can get the constants over on this side, and what I see then is I have negative k over m times x equals this derivative, or second derivative, d squared x dt squared. Okay, and what I'm showing here is that a function, this is the function position as a function of time, is multiplied by some constant is equal to its second derivative. So if we're thinking of a general solution to this second order differential equation, the general solution says this has to be, because remember we'd be solving for this x, the general solution says this function has to equal its second derivative but negative. Okay, so if we look at this, if we look at these functions that we have established over here, this function says when x is equal to 0, the function's equal to some maximum value. So we know that this is going to be some sort of cosine function, cosine of x or theta. This, of course, is going to be negative sine of x, and then this one is the flip of the first function, which is negative cosine. So we see that if we were solving for this x function, we're saying that it has to be the negative of that function is also its second derivative, and that makes sense here because the second derivative is the negative function of the function itself. So we know that the solution, the general solution to this second order linear differential equation is going to be equal to something to do with y is equal to cosine of x, or x is equal to something cosine of t. And what we're going to do in the next video is tailor this function to actually meet the credentials of having these constants and any sorts of shifts that we might need to use. So we'll take a look at that in the next video.